The main goal of quantum error correction is to create protected logical qubits better than the physical qubits that they're made out of.
So is that why on the cover of the Nature paper when this was published, you kind of have those sort of donut-shaped things?
The code must have high error threshold, low overhead, sufficiently small size, maybe a few hundred physical qubits.
You know, these LDPC codes can actually have logical error rates that are comparable with the surface code while using an order of magnitude fewer physical qubits.
Hello, my name is Abby Mitchell, and this is our Quantum Paper Review series. Today, we're going to be discussing a paper called High Threshold and Low Overhead Fault-Tolerant Quantum Memory. This paper was published in Nature in March 2024 and was actually chosen to be on the cover of Nature, which is pretty cool. Today, I'm going to be speaking to two authors of that paper, IBM Fellow Sergey Bravyy and IBM Senior Research Scientist Ted Yoder. To understand the methodology and the implications of this work, we're going to be sitting down and asking some questions. But before we do that, let's first understand a bit more about the paper and what it's talking about, starting with explaining the title. So let's take a look. The title is High Threshold and Low Overhead Fault-Tolerant Quantum Memory. This can be a bit confusing, so we're going to break it down piece by piece, starting with quantum memory. In classical computing, the term memory refers to how a computer stores information in binary states, zeros and ones. And quantum memory is talking about the same thing, but for information stored as quantum states. Specifically, the title mentions fault-tolerant quantum memory. In quantum computing, it is a real challenge to keep qubits stable enough to hold their quantum states. Often the qubits decohere and we accumulate more and more errors as the computation goes on. To achieve fault tolerance means that the error rate of your computation is, if not nothing, then so negligible that it doesn't affect the final result. One popular area of research that focuses on this goal is the development of quantum error correcting codes. In this paper, the authors developed a new set of error-correcting codes, part of a family of codes known as low-density parity-check codes, or LDPC codes for short. Okay, let's take a look at another section of the title, High Threshold and Low Overhead. In this context, high threshold is referring to the fact that these LDPC codes developed by the team offer a relatively high threshold of about 0.7%. Put very simply, the higher the error threshold, the more errors on the physical device the codes can correct for. So an error threshold of 0.7% means that if your physical qubit errors are less than 0.7%, which is feasible error rates for today's devices, then these error-correcting codes could be effective. For comparison, one of the most successful and famous codes to date, called surface code, has an error threshold of 1%. Lastly, to understand what we're talking about with the low overhead part of the title, we need to understand encoding efficiency or encoding overhead. The basic principle of quantum error correction is that you can use a large number of imperfect qubits to correct the errors on a smaller subset of qubits. So if you have a quantum experiment that requires, let's say hypothetically, 20 perfect qubits, or in other words, 20 logical qubits, then you could use perhaps 100 imperfect qubits plus some quantum error correcting code to get accurate results for those 20 logical qubits. So encoding overhead refers to how many physical qubits you need per logical qubit in order for your error correcting code to work. In this paper, the researchers were able to come up with error correcting codes with very low overhead. In one calculation, they were able to encode 12 logical qubits using 288 physical qubits, whereas surface code would have required about 3,000 physical qubits for the same performance. So, in short, what the researchers did in this paper is they developed a set of LDPC quantum error correcting codes that work at a similar error threshold to the current best performing surface codes, but with a much lower overhead in terms of the number of physical qubits required. Okay, now that we understand a bit more about the paper itself, let's dive into the interviews. Hi Ted, welcome to the studio. Thank you so much for being here. Before we dive in, would you mind just introducing yourself?
Right, so I've been a research scientist at IBM for about 6 years, and my focus right now is on quantum error correction.
Hi Abby, and thanks a lot for hosting this interview. Yeah, so I'm Sergey Bravyy, and I'm a researcher at IBM Quantum Group. And my interests include quantum computing theory, for example, error correction, algorithms, and complexity theory.
Great. Let's dive right in then. Before we get into some of the more complex details of the paper, do you think you could just explain for our viewers what error correction is and how does it differ from error suppression and error mitigation?
Yes, so let's begin with classical error correction, and it's a fairly simple concept. Let's say that you compose an email and you made a typo in some sentence. Then the person who reads the email would be able to spot the typo, and this is some sort of error correction. So human language has a lot of redundancy, and so each letter is correlated with adjacent letters in a certain way. So if there is a typo in some letter, you can easily spot it because it violates these correlations. And quantum error correction works in a similar way. So we introduce a redundancy in a way that we encode quantum states. And this redundancy leads to certain correlations between qubits that we can measure. We call these correlations parity checks. And if some error occurs on some qubit, it violates these parity checks, and we can detect this. So if we put together sufficiently many parity checks, we get enough information to identify error and correct it.
The main goal of quantum error correction is to create protected logical qubits that are much better than the physical qubits that they're made out of. And you actually make a big entangled state out of these physical qubits, and within that are some logical qubits. The logical qubits are not localized on just a handful of physical qubits, but they're actually spread out over this entangled state. And one thing this means is that if you have a few physical qubits with errors, you can still recover the logical information. And so in practice, how that's actually done is you measure certain properties of the state, parity checks or stabilizers, and we actually feed that information into a classical algorithm called a decoder, and the decoder will tell us what errors it thinks occurred. It will give a good guess.
For quantum, in the quantum case, we have two types of errors. We have bit flip errors, which are similar to classical typos, but we also have phase flip errors that destroy quantum superpositions. So these errors map quantum state to classical states, which we don't like. So we have to be able to correct two types of errors at the same time.
Does the error correcting codes that you've used in this paper account for both of those types of errors?
Yes, we can correct both a bit flip and phase flip errors by these codes.
From what I've been reading from your paper and just general error correction resources that I've been looking into, I see that there's this type of error correcting code called surface codes, which are pretty popular in the field at the moment, but the codes that you folks created for this paper are called LDPC codes. Can you explain to me what the difference is between these two approaches?
Yes, so actually the surface code is one particular example of LDPC codes.
And so the specific codes you created are a different type of LDPC code?
Yes, this is another example of LDPC codes, but it's more efficient because we can pack more logical qubits into the same number of physical qubits. LDPC stands for low density parity check code. A parity check tells us whether the number of errors on a certain subset of qubits is even or odd.
Okay, so you know that there's either going to be 10 errors or 11 errors?
Yes, exactly.
Okay.
So this is only a partial information about the error, but if we have many parity checks, we can combine this information, and this can be enough to correct the error.
All I actually need to do to specify a code is tell you what parity checks to measure. And it would be nice if the parity checks I told you to measure were not too difficult to measure. So
can you give me an example of what that might be?
Yeah, exactly. So the parity check should not act on too many of the physical qubits at once. You shouldn't have to talk to too many at once to measure this parity check. And also the physical qubits that you have shouldn't be involved in too many of the checks. So if you have those two properties, then you actually have an LDPC code. So that's what low density parity check means. It turns out that the surface code actually is a low density parity check code. Because every qubit in the code is involved in 4 parity checks, and every parity check involves 4 or fewer qubits. Crucially, the surface code only encodes 1 logical qubit. No matter how big you make the code, you only get 1 logical qubit.
Right.
And this fundamentally differs from general LDPC codes. As you make a general LDPC code bigger, you get more logical qubits inside.
Okay. So in order for these error correcting codes to work, and forgive me, I'm not really an error correction expert, it requires some fundamental changes to the hardware. It's not just a way of coding your program. You actually have to make changes to the hardware to be able to do this correction.
Yes. So first of all, we have to introduce a redundant encoding that I mentioned. Mm-hmm. So say if we want to encode only 10 logical qubits, we might need say 100 physical qubits to have enough redundancy.
And error correcting codes like this, they're not something that we've really yet implemented on real devices yet. At the moment, it's more sort of in the theoretical space. Is that correct?
We've implemented small error correcting codes. Codes that can detect or correct one qubit error. We even have some experiments where we achieve beyond break even, so beyond the physical qubit error rates with our logical qubits.
What does that mean exactly?
The logical error rate depends on the physical error rate of your qubits. If you have really bad qubits, then it could be that the logical error rate is actually worse than your physical qubits. If you have really good physical qubits, then the quantum error correcting code will sort of correct the remaining errors that exist. And so your logical qubits will be better than your physical qubits. And so there's some crossover point there where the logical qubits start outperforming the physical qubits.
Right, okay.
And that is a break-even point, or sometimes called a threshold.
So can you tell me a bit more about the specifics of the LDPC codes that you folks invented for this paper?
So each quantum code has several parameters. For example, one important parameter is a code distance. So it measures the number of the minimum number of single qubit errors that can destroy encoded state. For example, if we say that a code has distance 5, it means that you can detect less than 5 errors, no matter where these errors happen.
And what was the code distance for these codes you developed?
So we give several examples of codes, and one example is distance 12 code that encodes 12 logical qubits into 144 physical qubits.
And that is significantly better than surface codes.
Yes, so it's roughly 10 times more efficient than surface code if you look at how many logical qubits you can encode.
Amazing. And you called them bivariate bicycle codes, or BB codes for short?
Yeah, so this term is not super important. I guess we need some theory, coding theory background to make sense of it.
You talk about the error threshold for the codes that you created, and that threshold is 0.7%. Why is that a significant number?
So we usually describe random errors by the error rate. Say if the error rate is 1%, it means that there is a chance of 1% of having an error on each particular qubit.
Okay.
And so if we have such random errors are more close to what we have in the lab, in the actual quantum device, as opposed to worst case errors. Error threshold tells you the maximum error rate that the code can tolerate.
I see. So for error correcting codes, if you have a higher threshold, does that mean essentially the more noisy your computer can be when you can still use those codes effectively on it?
Yes, exactly. So we would like to have codes with a very high error threshold.
Right, okay.
For example, the Surface code has about 1% error threshold, and BB codes from our paper have roughly 0.7%.
Okay, so that's pretty good then if it's that close to, because Surface codes is the most popular one at the moment, right? So 0.7 being quite close to the error rate that the Surface codes has.
Yes, that's correct.
Great. Okay, let's take a look at figure 3, and can you tell me a bit about the performance of these BB codes that is sort of demonstrated in this diagram?
Right. So here we're showing the results of simulating the bivariate bicycle codes under a certain noise model and with a certain decoder. And in this noise model, every physical component in the circuit fails with an error rate P, and that's plotted on the x-axis. And then on the y-axis, we're showing the logical error rate of the protected physical qubits in the code. And I think one thing that's really important to notice and is like an indication that error correction is working is that a small change in the physical error rate can lead to a very large change in the logical error rate. So if you have an order of magnitude lower physical error rate, you actually get several orders of magnitude lower logical error rate.
And what is the difference between part A and part B?
Part A, we're just showing a variety of bivariate bicycle codes. In part B, we're showing one bivariate bicycle code, this 144 qubit code, compared with a variety of surface codes with different amount of error correction potential. What we point out here is that the LDPC code, the 144 qubit code,
that's this black line,
that's the
right?
black line, is right where it should be compared with these surface codes. So it has an error correcting performance, or what we call a code distance, of 12, and that's lying right between the distance 11 and 13 surface codes, while using a factor of an order of magnitude fewer number of physical qubits.
So essentially what this is showing is that the BB codes that you developed are within the range of how the surface codes perform, but crucially you're only using, 144 qubits, whereas all these others are using thousands.
Thousands of qubits, exactly. Yeah. So in red and green are parity-check qubits, which we use to actually measure these parity checks. So they must communicate with the data qubits and learn the values of these operators we want to measure.
And this diagram, it's in 2D here, but it's actually sort of a 3D shape, like it kind of wraps around, is that correct?
That's right. So these connections you can't lay out in just the 2D sheet of paper here. It's actually on the surface of a torus. So if you go off the top edge of this drawing, then you actually come back on the bottom edge, and there are some connections that do that. And
so
then likewise with left and right. If you go off the left edge, you come on the right.
So is that why on the cover of the Nature paper when this was published, you kind of have those sort of donut-shaped things, and that's sort of representing this?
That's right. This is a sort of natural way to visualize the codes. The other thing that I want to point out here is that while a lot of these connections are just between nearest neighbor qubits and sort of this square lattice, this grid, there are also these longer range connections, and there are 2 of those longer range connections per qubit. And this is, really the source of the efficient overhead of these codes, as compared with something like the surface code. The fact that we have these longer range connections.
When we just started working on this project, we had a kind of a wish list of error correction, what properties we would like to have in a quantum code. For example, the code must have high error threshold, low overhead, meaning that we can encode many logical qubits, sufficiently small size, maybe a few hundred physical qubits. Then we must be able to do logical gates on encoded qubits. And there are many other properties like qubit connectivity should not be too high and so on. And we discovered that these BB codes have kind of check marks for almost all items in our wish list, which is really great. And we are working on checking off the remaining items.
Great. So there's going to be further work that you're doing then to push these BB codes even further?
Yes. So we keep working on these codes. And I'm personally very interested in improving decoding algorithms. And decoding algorithm looks at parity checks that we measured and tells you a prediction of what an error has occurred on our physical qubits, so that we can correct it.
And is that, how important is that to the overall process of developing error-correcting codes?
Yeah, so the performance of a quantum code, like error threshold, depends on how good is your decoding algorithm.
I see.
So it's crucial that you optimized your decoding algorithm as far as possible.
Interesting. So then, if you could, theoretically improve the efficiency of your encoding algorithm, that could help you push that error threshold, above 0.7%.
Yes, that's possible. That we can improve the threshold further with better decoders. And also it's very important that the decoder has to be very fast, so we can do error correction in real time while qubits remain coherent.
Yeah, it would be a bit unfortunate if the qubits just died before you were able to correct any of the errors they were throwing. So I guess speed, efficiency, error threshold are all very important factors for making good error correcting code. Can you explain the significance of this paper in your own words?
Yeah, so I think this is a really nice example of an LDPC code family that we worked through all the details of constructing circuits, applying a decoder, and we found that these LDPC codes can actually have logical error rates that are comparable with the surface code while using a factor of 10 or an order of magnitude fewer physical qubits.
Huge thank you again to Sergey and Ted for coming to the studio to chat with me. Before this video, I really didn't have a great understanding of quantum error correction, and both of them really helped me to understand why this paper was so impactful and why quantum error correction in general is such an exciting field. We will leave the links to the paper and other resources in the description, so make sure to check those out. And if you have any ideas for new papers that have come out that you would like to see us review on the channel, leave us a comment below. Thanks for watching.